Yeah, you should get a thing to agree to here. Okay, now we're being recorded. We've already been had the attendance taken, so we can go back to the sharing the screen. Now, I'm going to start talking about this and then quickly get away from it. There it is. I've got several pages up. I don't know why that is. Let me try that again. So that's because, okay, I actually was trying to delete something on my own screen, and I've got to do something here for you, for me. Just a second. Sorry, I was trying to take the clutter off my own screen, and I deleted the page that we were on by mistake here. Hopefully that won't happen too often. So let me get that back. You set things up so everything goes smoothly, and then these kind of things happen. Where is that? That is here. Okay. Right. Now I got to go back and reset up the screen for you guys. Hopefully. Probably I have to do that again. Just one more moment here. Maybe. Sorry about the delay. Okay, maybe. Yes, okay, fine. Right, now you should see the same screen you had a minute ago before I deleted it. All right, so now on this screen, and we're going to get off of it real fast here, but on this screen, you should okay, I'm still trying to get this set up for me. Okay, on the screen, the important thing here is this line right here. And we're going to spend some time trying to understand this line. I just wanted you to see where it is. It's on page 1 in the middle of that stuff. And basically, we're going to be talking about limits, and we're talking about continuity. Now, what you do in the book is you study limits first, and then you do continuous functions because they have certain special limit properties. However, it turns out that continuity is the more general thing. And so continuity, if you learn the epsilon delta for limit definition and you learn the epsilon delta for continuity definition, it's the same definition almost, except for the last thing right here. So those of you who had some calculus before, if you did an epsilon delta definition of limit, for limit you'd have an L right here. And for continuity, you have the function value here. And for some people, they think that's the only difference between the two, but it's not the only difference. So I'm now going to leave this screen share, and go over to the different screen share, which has got the book picture on it. But what I want to do is get a blank piece of paper and start talking about it. So what we're basically trying to do, and for us, most of the things we do are going to be on some kind of a graph. And most of the things we do are going to have some kind of a curve on the graph. Now, what I just drew, most of you, if you were asked outside of math, is that a continuous thing I did, a continuous curve? And the answer is yes. When I did this by drawing it without lifting my hand off the paper, I made something we like to call continuous. Okay. Also, it's connected. And connected is another word we use to say it's not in pieces. It's one piece. So if I picked up one end of it, the rest of it would come. So if I pick up one end of a hose, the rest of it comes. If you start carrying the one end, you'll get all of it if you have enough strength, if it's not that long a hose. Anyway, you know about that. Now, however, we have pictures where when you draw the picture, maybe the thing has got some break in it. Okay, and so continuity is studying things like this, and limits are involved, but limits come in more for things like this, because this is not in one piece. And to try to study the difference between the two kinds of curves, we've got to get more careful into things. And the other word I'm going to use here is what we're interested in a lot of times is called a local behavior. What's interesting with this particular thing is why it's broken, is where it's broken. Whereas this one seems to be globally sort of the same. I mean, this might describe a hill or something. If you look out on the horizon, you might see something like this. So there's differences. Anyway, I'm going to write down that definition, and I'm going to try to explain it as we write it. But the definition I'm going to write now is different from the one in the pages that you thought was terrible, because I'm going to be using all symbols here. Now, because of our study we did on a little bit of logic, this upside down A is a universal quantifier. It means for every. And depending on the English, if you're good at English, it could be for all, for every, for each, for any, okay? Because we can change the second word to kind of make careful distinctions in the sentence. We don't worry about that so much in math. We can replace any of those words with any others. It means all. This epsilon, we use the epsilon specially here is a Greek letter, and we use a delta. This is the fifth letter, as I said the other day, and we need a delta. This says take a number, a positive number. You decide what it is, anything you like. You can make it big or you can make it small. For the purpose of calculus, this is usually small. But I don't know what small is. Small is relative. What's small in life may not be small in a microscope, okay? What's small in a microscope might be really small in life, but what is large in a microscope might still be small. Now, my father decided when I was about 3 years old, and I shouldn't tell you this story, but I tell stories about myself because I know they're true, not because I want you to know about me. But when I was very young, my father, my father never had any money, but he did, we did go fishing some. And my father, we caught fish. And my father was cleaning fish one day that we had caught. And I asked him a question, which I don't remember actually. I remember the scene actually, because it was the first time I ever saw somebody clean fish. And that's something that was sort of dramatic for me at the time. I don't remember the conversation, but he later told me when I was older something I said, which kind of astounded him at the time. And he decided maybe this dumb kid's not so dumb after all. Parents always want their children to be smart. That's why all your parents are proud of you, because you're in honors class. I'm sure if you tell them that, they'll all think, ah, yes, that's what I always wanted my child to be. Anyway, I asked my father when he was cleaning a certain fish, was it a big one or a little one? And my father tells me there were other people there that thought that was a dumb question. But my father realized it was actually a smart question, because he realized that I realized that one fish size might be small for that fish, whereas it might be large for another fish. So a large bluegill, if you go for panfish in Kansas, a large bluegill might be a small bass. And my father realized I was differentiating between species. And he thought, that's a smart kid. Now, I kind of disappointed my father the rest of my life. That may have been the only smart thing I ever said. Okay. But large and small are relative concepts. It depends on what we're comparing to. So when I take an epsilon here, it's anything that's positive. It could be large, it could be small, depending on the circumstances. For calculus, we usually want to talk about small, because, for example, here we're interested in what happens near this spot. Okay, but we have to define what near is. That's what we're trying to do right now. So you take an epsilon, then the next thing here is there's a delta. 2 Greek letters. Now you can call them P and Q if you want. It doesn't matter what we call them as long as we stick with it. Now, this says there is at least one. This is the word for some. And what we're doing is we're saying for each of these, there's one of these or more. Okay? So, for example, for each player on a team, there might be one ball. And the ball is relevant, it's related to the team. Okay? So, for each one of these, there's one of these. Like in teams, they have people who, well, when I was, we probably changed these words now because of all kinds of reasons, political correctness and all that. But when I was young, we called people that assisted a team water boys because they were usually male and they usually were involved with cleaning and stuff. And anyway, we call them water boys. That's probably a bad word these days. I'm being recorded now, so I'm probably, this is my last day to teach. But anyway, for the team, we may have had one water boy. And we could have said, for anybody on the team, there is one person you go to. Or maybe if we update that a little bit, maybe it's a medical doctor. So for each person, there's a medical doctor. Now, it might be the same person, it might be different. But for each person, there is one of these. That's what this is linking up. Okay? And then we have a couple of words which we can also symbolize, but I write it in English now, such that. So you tell me about this number, then there is an associated number with it, hopefully, such that, now I got to tell you what. The next thing is a for all again. And now I have just come to the place where I realize that I can't say this because I got a blank here, because I want to talk about everything in some set. So what's involved here is sets. But I kind of forgot, I didn't really, but I kind of forgot to put the set first. So what are we talking about? Well, let me go down here a little bit and say we're talking about functions. Okay? And functions for us are going to have domains and ranges. And we said the other day, we're going to write a function. We're going to write something like this. If I write something like this down, okay? Now, I should actually write this first. What I should say is, let's take a set of real numbers and call it D, as in dog. Okay? So elements of the set are going to be elements of D for the whatever D is. I just decided maybe it's everything between 0 and 5. I make a decision, I decide on something. And then I'm going to have a function that takes each number in the set D and gives me a real number. Usually we specify that with a formula. So let's say here, let's suppose D, make it simple. Let's suppose D is all real numbers. That's not much limitation at all. We could do something different. And let's suppose f of x is x squared. Now you know all that already. And a lot of times you'll see this last thing here without anything else. Somebody will just say f of x equals x squared. Let's talk about it. You guys sort of know that if we graph it, you get this curve and stuff, and we call it a parabola and all that. All that kind of stuff we're going to forget, kind of, in a way. We know all that stuff in our background, but we're going to try to prove it. We're going to try to verify everything and so forth. So right now, I'm not really assuming you know that this picture is accurate or inaccurate. Don't care, because we're not going to use the picture too much yet. We're going to try to find out that we can trust the picture that we use. Instead of just having a picture and relying on it, we're going to try to show you how to trust the picture. Okay? So anyway, I have this formula. Everybody knows this formula. And you guys all know, not all of you, some of you may know limits and stuff already. I don't know. But what continuity says is I want to get close to something. So let's suppose that we get close to 3. Now my phone is ringing. That's too bad. When you get close to 3, it'll ring about 5 times and then we won't answer it. Isn't that nice? Okay. We're going to talk about getting close to 3. And what we want to do with continuity is say, when x gets close to 3, what does f of x get close to in the formula? Continuity says that it gets close to 9, that you're allowed to stick the 3 into the formula to get the answer. And so the continuity involves the relationship between 3 and 9 given to me by this formula. We'll talk more about that in a minute. But now I have a domain. So in the problem I have, I'm taking any real number, anything in the domain, which in this case is not very restricted. And then I have an if-then sentence. So this says, for every epsilon, there's a delta that's always the same thing every single time, such that this is always the same. What changes is what we put here. It depends on what the domain of the function is. So you got to know the domain of the function in order to do this. And we have an if-then sentence. That was something we talked about in the logic, if you remember. This is a conditional sentence. And the if-then sentence says, if x minus 3 is less than delta. Now, we picked any real number. This says if that real number's distance to 3 is less than delta. Now, delta was the number you picked up here. Okay, so delta is considered, when you get to this step, delta is considered to be a known quantity. You're supposed to know how big the number is so you know how far off this can be. So this says if you are close enough to 3, that's what that tells you, then f of x, okay, minus whatever you think the limit is, sorry, not the limit, whatever you think the answer is for continuity. This is, we're saying the distance between the f of x in the formula for that x, this is not a variable now, this is a single thing. That thing, which is close enough to 3, this is the distance between the thing and 9, and that's less than epsilon. Now, the epsilon was what you decided was small or big at the beginning. At the end here, we have to get that close. So if you say epsilon is 5, then this says the distance between this thing, which in our problem will be x squared, the distance between that thing and 9 is less than 5. If you say epsilon is 1/1000th, then this says the distance between the x you pick squared and 9 is less than 1/1000th. So this is a measure of how close this number, and it's not a variable, this is a fixed thing, how close this thing is to 9 when you pick it this close to 3. Now, pictorially, if this is a graph of the thing which may not be, and I go to 3, and on the graph you have f of 3 is 9 by the formula. If you're telling me that the limit, if you're telling me the function is continuous at 3, I'm used to doing limit first too. If you tell me the function's continuous at 3, it says when I get close enough to 3, all the values, the heights, get close to 9. That's what you're telling me. And the idea here is for you to set how close you need to be. How close, my picture. How close do you need to be to this height so that things here get that close? So what we do is we put a little band around the number you claim is the right answer. That's an epsilon band, so-called, we'll get to that. And then I have to decide how close do I have to be to make an x here so this x goes up into this band. And we'll be talking much more about this, okay? But I have a different problem I want to ask you. We worried about domains. What if my function is f of x is x, okay? But suppose the domain is just 1, 2, 3. Now, what's the graph of that? Well, the domain is 1, 2, 3. It's 3 points. each value goes to itself, so I have 3 points on the graph. That's my graph. How many of you think this is a continuous function? I see one. I only have 2 pictures of people. I have a Mary who shook her head no, and I don't need to tell you that. I mean, I don't want to tell everybody that because maybe you're wrong. And I have Michael who didn't answer. Okay, that's only two people I can see. Maybe I can go over and see more of you.
I'm still in the notes.
This is a much more interesting screen. Okay, so is this a continuous function or not? By the way, that's a tautology. You know, is it continuous or not? The answer is yes. Okay. Now, Mary shook her head a while ago no, because I was on the other. I was looking at other people, and Mary is one of them. None of you answered here. I got some other people up here. It turns out this is a continuous function. Now, why? Well, I actually can prove using the epsilon stuff that it's true. But more than that, we don't even do that. What we say is, if I have a point in the domain of the function, which is not an accumulation point. Remember a few days ago we talked about accumulation points of sets. In other words, if I have an isolated point of my set, this particular set is all isolated points. Every point is isolated. A function is automatically defined to be continuous at an isolated point. And since this function only has 3 points, and each of them is isolated, this is what we call a continuous function because it's continuous at every point. Let me change this a bit. Suppose the domain is the numbers between 0 and 1 and the number 2. Now the domain is 0 to 1. It's all of these numbers, and it's the number 2. Okay? So this is my domain. No matter what function I define with this domain, it will be continuous at 2. Now, whatever the function is going to give me some value. And so this, what I put here is this is a dot on the graph. No matter how I define this over here, this function is continuous at 2. So functions are continuous at any isolated point. What about the rest of these points here? All the rest of these points are accumulation points, right? This is what we decided the other day. Let's remember what accumulation point is. Take any point in the set, I call accumulation point. The question is there some neighborhood around the point which is only in the set? And no matter which point you pick here, except the endpoints perhaps, you have accumulation point. And even if you pick I beg your pardon, you erase what you heard me say from the video you watch again. Accumulation point says every neighborhood contains 1 point besides the center, not every point. So the boundary points here are also accumulation points. Now, the reason to do continuity first is because we need to include isolated points in our definition. If the point is an accumulation point, then we can talk about the limit of the function at that point. Now, why does the book talk about limits first? Because the book never talks about isolated points. The domain in the book is always going to be an interval. Every point of the interval is an accumulation point, so the author doesn't have to split hairs between things that are isolated and things that aren't because he doesn't talk about them. So he does limits first and then does continuity. And the only difference between limits and continuity for the author is replacing the letter L in the limit with the letter f of x naught in the continuity. So the two concepts for accumulation point are essentially the same. Okay? But almost all the functions we study are continuous, or at worst, continuous in pieces. So most of the time we'll be talking about continuity, and therefore that's more important than limit, because it's only sometimes we have to refer to the limit. Okay? Okay, so now let's try to do something simple. Suppose I have a function f of x equals 3. What's the domain? I don't know. I'm going to make everything in the real numbers f of x equals 3. This is called a constant function. Now, I hope you know what the graph of it is, but again, I'm not worried about the graphs. We're going to teach you how to graph. Okay? If I do know the graph from high school, I would make a straight line like this at height 3. But I don't care about that right now. Although we're going to use it in a minute just to illustrate stuff, because you want to use it, but you don't want to depend on it. So what I want you to use is all your previous knowledge, but I don't want you to depend on the previous knowledge, because you might have been wrong. How do I prove that f is continuous at 1? Well, by the way, what's f of 1? F of anything is 3. So what's f of 1? 3. Okay? Sounds like a hard question, but it's not. Okay, so what am I trying to show? I need to show for every epsilon from that definition. Now, to show that f is continuous at 1, I need to show for every epsilon there's a delta and so on. So how do you do that? You always take an epsilon. Now, I have no idea what the size is. Remember, we can take anything. You always start out in trying to verify this by taking one. We take one. I have no idea how big it is. I'm going to relate everything else to it, but I don't care how big or small it is. I just got something. Now, once I have it, it's fixed. Okay, this is a fixed number. All right, I have to choose next. Remember, for every epsilon there's a delta. I have to choose the delta next. Now, sometimes that's difficult. And I have to choose it so that once I do that, after I do that, now I haven't done it yet, I know, but I'm trying to get ahead. I'm trying to predict what happens if you drive your car 60 miles an hour into a wall. You don't have to do it. You can think about what is going to happen ahead of time, hopefully. Okay? Because it's not smart to drive a car into a wall at 60 miles an hour, unless you're over in our Institute for Aviation Research where they do such things. Hopefully nobody's in the car. Okay? Anyway, I need to take something in a domain, anything at all. Our domain is everything, so I'm taking something. And once I take it, it's fixed. It's not a variable anymore. When I say let x be a member of R, x is now supposedly a known number. We use x because we'd like to be able to use this thing for no matter what the number is, but the point is it's a fixed number. And now I'm going to assume that this number I picked, its distance from 1 is less than delta. Now, I know I haven't picked delta yet, but this is what you would do every time. You're supposed to pick delta, you take something in the domain, and you assume that thing is that you picked is within delta distance of 1. This is spelling out a closeness to 1 right here. I'm within I'm within delta of the number 1. And you have to show that the f of x minus the f of 1 is less than epsilon. This is what you have to show. So part of what I'm doing here, I know it's off the screen, part of what I'm doing here is I'm telling you what you've got to do. Now, so here's the key to how you prove stuff like this. You always look at the end that you're trying to show to see what's going on. In this particular case, what's going on? What's f of 1? 3. What's f of x?
3.
F of x is 3. So what do I have to show in this problem? I have to show that 0 is less than epsilon. So in other words, I wouldn't write all this down normally. I'm showing you what to do. You go right away to this end part and you see what you have to do. You see what you have to do to help you pick the delta. In this case, I have to show 0 is less than epsilon. What am I assuming? The 0 is less than epsilon. So I got nothing to do. In other words, what I have to do is always true in this easy problem. If what I have to do is already true, I don't have to do anything. But in order to do the proof, I have to find a delta that works. How close do you have to be to 1 for 3 minus 3 to be 0? You don't have to be close at all. So let delta be the cube root of 737. I don't care what it is. All I have to do is pick any positive number in this problem. Each problem is different. In this problem, I pick anything at all.
Sorry to interrupt, but Hannah got disconnected. Can you let her back in?
Ah. Thank you. Hannah, I hope you're back. Don't know how much you missed, but you can always watch the video. So anyway, the point is, in this easy problem, it doesn't matter what I pick here, no matter how close I get to 1. Now I go back up here to this picture which we drew, which we're not supposed to know about yet. If I have the number 1, how close, what x do I have to pick so that f of x gets close to 3? No matter what x I pick, f of x is 3. Therefore, I can pick any x at all. It doesn't matter in this problem what x I pick, it's within the boundaries of what I'm doing. So this particular proof is so easy, it's hard. Meaning, you don't have to be careful about delta, but you do have to pick it. It doesn't matter. This is a crazy number. I don't know what it is. Pick 5. Pick anything. Doesn't matter. You just have to pick something and it works. Done. Therefore, we proved that f is continuous at 1. Okay? Now, I'm going to do something a little more challenging. Suppose f of x is x. Not much more challenging, but a little bit. What do you think happens to f of x as x approaches 3 again? So now I'm going to put x naught equals 3 because I like to use x naught. Sometimes the book likes to use a for numbers, but I like x naught for other reasons we'll see later. Anyway, suppose I want to get close to 3 again. When x gets close to 3, what's f of x gets close to?
3.
3. Who is buried in Grant's tomb? If x gets close to 3, what does f of x get close to? But f of x is x. So I'm guessing to show continuity, what I have to do is show that, I'll just say it here in words, when x is close to 3, no, x is close to 3, f of x is close to 3. That's what continuity is doing. It's close to f of 3, which turns out to be 3 in this case. So how do I prove it? Take an epsilon. choose a delta. But I said, oh, we don't really do that. We get ahead of ourselves. What you do someplace else is you look at the then part of the if-then sentence. The then part of the if-then sentence is this. And you don't know all that yet, but you will. This is the then part. This is what I have to show once I get the whole thing set up logically. What is f of x in this problem? It's x. What is f of x naught in this problem? What's f of 3? It's 3. So what do I have to show in this problem? I have to show x is less than 3. Now, once I've chosen delta, what do I do next? I take something in the domain, which in this case is anything again, and I assume that 0 is less than x minus x naught is less than delta. So now I've got almost all of it written down in the proof. You take an epsilon, you choose a delta. I haven't done that yet, but I got to. You take a point, you assume that point is within a certain distance of 3, because that's the x naught in this case. And I have to show that x minus 3 is less than epsilon. Now, this is the part that's sometimes hard for people until you see it, then you'll wonder why you never saw it. I've got to pick delta so that after I get done picking it, when x minus 3 is less than delta, then x minus 3 is less than epsilon. I don't get to pick epsilon, but I get to pick delta. I can pick delta to be any positive number so that when x minus 3 is less than delta, then x minus 3 is less than epsilon. How do I pick delta? You pick it to be epsilon. You're given epsilon. You choose delta to be epsilon. You assume 0 is less than delta, and I have to prove it's less than epsilon, but if delta equals epsilon, I've done it. So the proof now would be then x minus 3 is less than epsilon, and I have proved that the function f of x equals x, given that, that's the identity function, is continuous at 3. So this is not as simple as the constant function. For the constant function, I can pick anything. For the identity function, how close do I have to get to 3 to get close to 3? Well, however close you pick is what you can use. In this particular case, if we had a graph, I presume you know, is a diagonal. If you get close to 3 one place, it makes a square. So that's why getting close to 3 is the same in the x and the y direction. Anyway, but look what we can do. Suppose we throw away 3 and talk about continuity at any x naught. Any x naught. What do I have to prove? What is f of x naught? It's x naught. I have to prove that x minus x naught is less than 3 when x minus x naught is less than delta. What do you do in the proof? You pick delta to be epsilon. Doesn't matter. We just proved the function's continuous everywhere with the same little proof. So you try to do it in general, if you can, so you don't have to do it millions of times. Now, I want to get off this written stuff and go back to the printed version. I'm hoping this will make sense to you in time, not maybe at immediately. But now, on your page here, I prove right here that the constant function, now, instead of 3, I put c here. If f of x is always c, constant, a number, I want to prove that it's continuous at any point. Now, I have to have in mind to do that what happens to f of x naught, but f of x naught is going to be c. So the proof is take a number, take an epsilon, choose delta to be 1 or anything else. Remember, in this constant function, we can pick it to be anything. choose delta to be 1, choose delta to be epsilon, doesn't matter what it is, see? Then delta is positive. Let x be in real such that this is true. And what about this? This is equal to c minus d, which is always 0, which is less than epsilon, and you're done. Now, what in the heck is this right here? That's a symbolism which has been used since the Roman days, Roman times. That is Latin for quod erat demonstratum. Demonstratum is a neuter word. That's a nominative case. Quod erat demonstrate. Erat is the word to be or is. It's a certain form of that. What this says is quod erat demonstratum in English is that as what is supposed to be demonstrated. In other words, we're done. In other words, this is what needs to be demonstrated. Okay. Now, it means the proof is over. And it has meant that for 2,000 years for people who involve Latin. Okay. Quod erat demonstratum, that which was to be proved, meaning we're done. I learned that, by the way, not in math. It was used. I never knew what it meant. Nobody I knew what it meant. I learned that when I watched the movie The Guns of Navarone, which came out in about 1966. And one of the people in it was David Niven. And David Niven, when the good guys were shooting the bad guys, once the deed was over, David Niven says, QED. And everybody, all the other soldiers looked at him and he said, as that is which needs to be done. And I thought, I know what we're talking about here. Okay, and I took it back to math class because now I knew. I was able to tell my friends, I know what that means. I wouldn't tell them, of course, because I wanted to be smarter than they were. Anyway, I'm on tape and I should go in and wipe that off. The identity function is what we did next. And here's a little proof of that written out for you. Okay. Then we have linear functions. We're going to get more complicated. Now, we're not going to get much more complicated, but what I'm trying to do here is to show you how it gets worse. So when I have this function, you no longer get to choose the delta to be epsilon anymore like I did right here. When you get down here, you have to choose the delta for these kind of functions to involve epsilon over a, because the function involves an a right here. Okay? And it turns out it's a little more complicated. Same proof. Take an epsilon, choose a delta, let this happen, then work out that it's less than epsilon. Same proof, but it's more complicated because the function is more complicated. What about the next one? Absolute value. Is that continuous? Is the absolute value function a continuous function? In this case, you get to choose delta as epsilon again, except the verification's tougher. Because when you stick f of x, it's absolute x, and f of x naught is absolute x naught, and you come to grips with the absolute value of the difference of absolute values. Now, in the notes I handed you last 2 weeks, one of the problems you had, not problems, one of the things you had in the notes was several lines about the properties of absolute value. I gave you notes in which you have the absolute value of the sum is less than or equal to the sum of absolute values. And the absolute value of the difference is less than or equal to, and so on. This comes from the notes I handed you. So what do you have to do? You have to know these things about absolute value to be able to make progress here. And it's harder because you have to know something to do this, but not much harder. Still one line. That can't be very difficult, but you have to know something here about absolute value. We're going to use that. And now we get to this one. This one's squared, okay? It's worse again. Look at the delta now. This delta is the minimum of two things now. That's complicated. And the statement takes a little bit more to write out, okay? Now, why is it complicated? Remember, I get to choose delta anything that works, okay? And when you do the then part, like I told you a while ago, when you do the then part, it turns out to be harder to do. And so I'm going to show you why here. Here's me trying to do the then part. F of x is x squared. F of x naught is x naught squared. So what I get is this right here. This is what I would look at before I do the proof to try to figure out what the delta is. So I write this down. That's what it is. What can I do with that algebraically? I don't know. I can factor it. Now, the absolute value of the product is the product of absolute values. So I can replace this with this. I'm just playing around with this when I first do it. And what am I going to know about this thing? By the time I get to this step, I'm going to know that this right here, I'm going to know this right there. I'm going to know that by the time I get there. Anyway, I'm going to know something about this thing right here. It's going to be less than delta. So I'm replacing this with something bigger. It's a product. So this times this is less than this times, see, this thing on both sides, I'm multiplying by something that's positive. It keeps the same sign. Now, here's the point. This is as far as I can go. I want this to be epsilon. I want it to be epsilon, but now it's got an X in it. Now it's not like, I can't pick epsilon to be delta. Now, let's suppose I did. Let's go right here. And I'm going to write that down on my page, and I'm going to translate that. Suppose you get to this step in your work, and you decide, because it's worked before, when you get to this step before, you pick it to be epsilon. That's what you've done up to now. The trouble is it's not that easy, but let me try to show you why. To do that, I have to get
Dr.
off.
Brady,
Yes, sir.
it's 1227.
Oh, it is. I'm looking, I saw 1221. I'm sorry, my 7 is hiding under my computer and it looked like 1. Thank you, sir. Okay, you guys got to figure that out, I guess, and we'll talk about it tomorrow. We've already taken your picture. Let me stop the recording, stop the share, and stop the recording.